1. Quantum theory, introduction and principles. 1.1 The failures of classical physics. 1.2 Wave-particle duality. 1.3 The Schrödinger equation. 1.4 The Born interpretation of the wave function. 1.5 Operators and theorems of the quantum theory. 1.6 The uncertainty principle. C. 1.1 The failures of classical physics. A black body radiation at max. Observations. 1. Wien displacement law. 2. Stefan-Boltzmann law. EV. Tentative explanation via the classical mechanics. Equipartition of the energy. Per degree of freedom, average energy equals kT. 26 millielectronvolts at 25 degrees Celsius. The total energy is equally partitioned over all the available modes of motion. Rayleigh and Jeans use the equipartition principle and consider that the electromagnetic radiation is emitted from a collection of excited oscillators, which can have any given energy by controlling the applied forces, related to T. It led to the Rayleigh-Jeans law for the energy density as a function of the wavelength. It does not fit to the experiment. From this law, every object should emit IR, vis, UV, X-ray radiation. There should be no darkness. This is called the ultraviolet catastrophe. Introduction of the quantization of energy to solve the black body problem. Max Planck, quantization of energy. E equals NH only for n equals 0,1, 2. H is the Planck constant. Cross-check of the theory. From the Planck distribution, one can easily find the experimental Wien displacement and the Stefan-Boltzmann law. The quantization of energy exists. See atomic and molecular spectra. Excitation energy. Photon absorption. Photon emission. H equals Hc/Phi. The emission and absorption of radiation always occurs at specific frequencies, another proof of the energy quantization. Mb, wave number. 1.2 Wave-particle duality. The particle character of electromagnetic radiation. The photoelectric effect. E. H. Metal. The photon H, left-right arrow, particle-like projectile. Conservation of energy half mv2 equals H. Equals metal work function, the minimum energy required to remove an electron from the metal to the infinity. Threshold does not depend on intensity of incident radiation. Mb, the photoelectron spectroscopy, UPS, XPS, is based on this photoelectric effect. B, the wave character of the particles. Electron diffraction. Diffraction is a characteristic property of waves. With X-ray, Bragg showed that a constructive interference occurs when equals 2d sin. Davidson and Germer showed also interference phenomenon but with electrons. Particles are characterized by a wave function. D. V. A link between the particle, P equals mv, and the wave, common natures. An appropriate potential difference creates electrons that can diffract with the lattice of the nickel. 1.3 The Schrödinger equation. From the wave-particle duality, the concepts of classical physics, CP, have to be abandoned to describe microscopic systems. The dynamics of microscopic systems will be described in a new theory, the quantum theory, QT. A wave, called wave function R, T, is associated to each object. The well-defined trajectory of an object in CP, the location, R, and momenta, P equals m.v, are precisely known at each instant t, is replaced by r, t, indicating that the particle is distributed through space like a wave. In Qt, the location, r, and momenta, p, are not precisely known at each instant t, see uncertainty principle. In CP, all modes of motions, rot, trans, vib, can have any given energy by controlling the applied forces. In the QT, all modes of motion cannot have any given energy, but can only be excited at specified energy levels. See quantization of energy. The Planck constant h can be a criterion to know if a problem has to be addressed in CP or in QT. H can be seen as a quantum of an action that has the dimension of ml2t1, E equals h, where E is an ml2t2 and is in T1. With the specific parameters of a problem, we built a quantity having the dimension of an action, ml2t1. If this quantity has the order of magnitude of h, 1034 Js, the problem has to be treated within the QT. Hamiltonian function h equals T plus V. T is the kinetic energy and V is the potential energy. Correspondence principles are proposed to pass from the classical mechanics to the quantum mechanics. Classical mechanics. Quantum mechanics. Schrödinger equation. Operator function equals constant times same function. The Schrödinger equation, SE, shows that the operator h and I/t give the same results when they act on the wave function. Both are equivalent operators corresponding to the total energy, E. In the case of stationary systems, the potential Vx, y, z, is time independent. The wave function can be written as a stationary wave, x, y, z, t equals x, y, z, it, with E equals h. This solution of the SE leads to a density of probability vertical bar x, y, z, t vertical bar 2 equals vertical bar x, y, z vertical bar 2, which is independent of time. The time-independent Schrödinger equation is NB. In the following, we only envisage the time-independent version of the SE. Or, the Schrödinger equation is an eigenvalue equation, which has the typical form. Operator function equals constant times same function. The eigenvalue is the energy, E. The set of eigenvalues are the only values that the energy can have, quantization. The eigenfunctions of the Hamiltonian operator H are the wave functions of the system. To each eigenvalue corresponds a set of eigenfunctions. Among those, only the eigenfunctions that fulfill specific conditions have a physical meaning. 1.4 The Born interpretation of the wave function. Example of a one-dimensional system. Physical meaning of the wave function. Probability of finding the particle in an infinitesimal volume d equals t states at some point r is proportional to vertical bar r vertical bar 2d. Vertical bar r vertical bar 2 equals r is a probability density. It is always positive. Wave function may have negative or complex values. Node. A normalization condition. The solution of the differential equation of Schrödinger is defined within a constant n. If is a known solution of h equals E, then equals n is also solution for the same E. H equals EH, n equals E, and NH equals NEH equals E. The sum of the probability of finding the particle over all infinitesimal volumes d of the space is 1, normalization condition. We have to determine the constant n, such that the solution equals n of the SE is normalized. B. Other mathematical conditions. R if not, no physical meaning for the normalization condition. R should be single-valued R if not, 2 probability for the same point. The SE is a second-order differential equation, R, and dr/doctor should be continuous. C. The kinetic energy and the wave function. We can expect a particle to have a high kinetic energy if the average curvature of its wave function is high. The kinetic energy is then a kind of average over the curvature of the wave function. We get a large contribution to the observed value from the regions where the wave function is sharply curved. 2/x2 is large, and the wave function itself is large too. Example, the wave function in a periodic system, electrons in a metal. 1.5 Operators and Principles of Quantum Mechanics. A. Operators in the quantum theory, QT. An eigenvalue equation, F equals F, can be associated to each operator. In the QT, the operators are linear and Hermitian. Linearity is linear if CF equals CF, C equals constant, and F plus equals F plus. NB, C can be defined to fulfill the normalization condition. Hermiticity. A linear operator is Hermitian if where F and R finite, uniform, continuous and the integral for the normalization converge. The eigenvalues of an Hermitian operator are real numbers, equals. When the operator of an eigenvalue equation is Hermitian, two eigenfunctions, Fj, Fk, corresponding to two different eigenvalues, j, k, are orthogonal. B. Principles of quantum mechanics. 1. To each observable or measurable property less than greater than of the system corresponds a linear and Hermitian operator, such that the only measurable values of this observable are the eigenvalues j of the corresponding operator, F equals F. 2. Each Hermitian operator representing a physical property is complete. Def, an operator is complete if any function, finite, uniform and continuous, x, y, z, can be developed as a series of eigenfunctions fj of this operator. 3. If x, y, z, is a solution of the Schrödinger equation for a particle, and if we want to measure the value of the observable related to the complete and Hermitian operator, that is not the Hamiltonian, then the probability to measure the eigenvalue k is equal to the square of the modulus of fk's coefficient, that is vertical bar ck vertical bar 2, for an orthonormal set of eigenfunctions, fj. Def, the eigenfunctions are orthonormal if nb. In this case. 4. The average value of a large number of observations is given by the expectation value less than greater than of the operator corresponding to the observable of interest. The expectation value of an operator is defined as 5. If the wave function equals f1 is the eigenfunction of the operator, f equals f, then the expectation value of is the eigenvalue 1. For normalized wave function. CP 305 in the book. 1.6 The uncertainty principle. 1. When two operators are commutable, and with the Hamiltonian operator, their eigenfunctions are common and the corresponding observables can be determined simultaneously and accurately. 2. Reciprocally, if two operators do not commute, the corresponding observable cannot be determined simultaneously and accurately. If 1221 equals c, where c is a constant, then an uncertainty relation takes place for the measurement of these two observables. Where uncertainty principle